Hello and welcome. I am Martin from Zurich, working at Ockajak here, and we shall talk about Scala. Now, this talk is aimed primarily at people who are experienced in Java, Java developers. If you don't have experience in Java, don't panic. It still should be fun and you should still learn some useful things, hopefully. A quick outline of the talk. So Scala, as you probably know, is a both functional and object-oriented language. It supports both paradigms. And we are just going to start with what we know about Java. We are going to mention the things which are the same, and then we are not going to mention them anymore. Then we are going to look at some basic differences between Java and Scala, how to go from Java to Scala. And some integration issues, how do we integrate the two. And then most importantly, and perhaps most interestingly, we are going to look at additional features. So what Scala actually gives you that's better or more or extra. And if the type permits, we might even look at some advanced feature. Scala has actually a lot of features, so we are not going to be able to cover everything at all, but hopefully the most interesting ones. Okay, so the similarities between the two, or shall I say identities. We are going to go over this section very quickly. Basic features, syntax and keywords are very similar. Most keywords are actually shared. Both languages use static type checking. They use exception handling. They use dynamic and single dispatch to implement polymorphism. This is all supported in both languages. Let's look at object-oriented features. As you very well know, Scala you have classes, interfaces. In Java, in Scala is the same except the interface is called trait. Otherwise, works the same way. Both support ad hoc polymorphism, otherwise known as meta overloading. Both also support parametric polymorphism. In Java, this is since version 5. So you have so-called generic programming. And you can also have things like access and mutability modifiers, private, public, final, and these things for fields and classes. Let's look at a little more high-level features. This is mostly stuff that was added to Java relatively recently, version 7, version 8. So both languages support functions as a first-order object. You can have anonymous functions, usually written as a form of lambda expressions, so-called. They support higher-order functions. That means you can have functions that accept functions as arguments. This all works. You have annotations, which is very nice. And both languages support runtime reflection. Last but not least, or last, let's look at the platform. Both languages have a reference implementation on JVM. I'm talking about the reference implementation because there are other implementations, both for Java and Scala, as you probably know. So that means you have your standard environment, Jar files, packages, imports, everything you are probably very well used to. And very importantly, it brings you the stability and the performance of JVM. Generally speaking, if you have something in Scala something in Java replaced with Scala code, you don't have to worry about stability and performance, except for some special cases. So you are good to go. And you have a famous documentation generator, JavaDoc, except it's called ScalaDoc, does the same thing. And last thing, with environment also come tools. So for Scala, you can actually use most of the build system that you can use for Java, like Gradle and Maven. There is also a new one called SBT. This is a Scala-specific one. The difference is that SBT actually uses Scala as its language. So you program your build in Scala as well, which has advantages and disadvantages. But you can use any of those. There is a very decent support for all kinds of IDE, IntelliJ, Eclipse, NetBeans, probably also some that I don't know. If you are not the IDE person, you can use editors. There are good support for syntactic highlighting, omni-completion, and different editors. This all exists. And also in Scala, you have a shell, also known as read evaluation loop. And in Java, this is not the case yet, but I believe in version 9, this will exist, so if I'm not mistaken. So this all works. This is all good. So this is a familiar environment already that you are in. Many things are the same. Now let's look at the differences. What is different? Now this part of the talk, when we talk about differences, we are going to look specifically at things that can be done in Java and how they are done in Scala. So no extra features yet. Still the stuff that we already have in Java. basic syntax. So one difference is that in Scala, being a functional-ish language, everything is an expression. Generally, syntax is almost the same. You have the curly braces and standard braces, round braces, everything you know, except you don't need semicolons, which I think is a nice addition. You can put them in there, but they are not needed. So normally, if you see Scala programs, you will not see any semicolons anywhere. And a very important point, Scala being functional, everything evaluates as an expression. Everything is an expression. Everything evaluates the value. So if you have a block of code, which is a sequence of statements, last statement in the block is the value of the block. That's something to remember. Then another very, very useful thing, which is relatively common in modern languages, you have type inference. This means that the compiler is able to infer the types of some variables, and you don't have to specify the type annotation explicitly. You can, but you don't have to. Sometimes it's useful to do that, but mostly you can omit, especially for local variables and that. But the type is still known. So if you are using, for example, the IDE, you can always ask the IDE, so what is the type of this variable? It's known, it's just hidden, you don't have to write it down. This speeds things up. So it's deduced by the compiler. And since those languages are actually, when it comes to the Java feature set, very, very similar, it's totally possible to translate the code automatically. There's a really wonderful tool. You see the URL here, code java2scala.com. You paste your Java code, it converts things into Scala. A typical use case that, oh, I want to solve some problem, oh, I go to Stack Overflow, oh, there is a solution in Java, copy and paste, boom, .scala, done. So this is what we do a lot. Okay, now let's start with some code examples. Method syntax, how do methods work? At first, you can see the example. It works, okay. You can see the Java example. I trust everybody understands this. This is trivial. So we have two methods. One actually causes side effects. It's a nasty one, and it's overridden from some class that was inherited. And it prints something, right? It has one parameter. Another one is pure. Actually, it doesn't do anything. It returns a number. You can call it many times. It will overreturn. It will not cause any side effects. In Scala, the syntax is very similar, just different that instead of void, here we have unit. The type annotation, as you can see, goes after the variable, not before it. So this function, we don't say it's unit here, we say it's here. This function method expression evaluates to unit, which means void, which means nothing. But unlike in Java, this is a proper data type, which carries no value. Also, you can notice that here, this method actually accepts lambda. This is one shortcut from the Java standard library. You can supply actually a function. Here, the syntax is that we put a lambda expression. It looks very much like one in Java, except we have equal sign instead of the dash. So it's a classic lambda expression. And the override is not an annotation, but it's a keyword this time. So very, very similar, as you can see, nothing very surprising. The second method, I just put it there to demonstrate that the syntax is a little more flexible, so you can usually get rid of all kinds of extra parentheses. You don't have to put the curly braces in, and you can just have and you also don't have to put the round braces after the name of the function. Because like, oh, this is a def, we define a function, and it returns a double, and happens to return a constant. But this is a proper function, proper method. Oh, and yes, you have to put the word def everywhere if you are defining a method. And as you might have noticed, last thing, everything is public by default in Scala, whilst in Java, you have to say it's public, which I think is an improvement because this is a very common use case. Private still works the same way as before, so everything is public by default. So this is just the basic method/function syntax. I think it's clear. We can look at some other syntactic constructs. So let's look at class and fields. We have here a simple class which has a simple constructor, it has a property, and it inherits from some interfaces. So this again should be a very simple example in Java. And when you create an instance, it actually prints something, a new instance, hello. In Scala, the syntax is a bit less verbose again. The most important part is how you specify constructor parameters, so you have to put them after the class definition. You can also have auxiliary constructors, which you will see later. But if you have properties, it's good to put them after the, and this will automatically generate basically the constructor. So then the virtual generated constructor would consist of filling in the mutable variable and running this println statement, which, as you can see, looks much like the static statement in Java. You can just put it into the class, and this will get executed when the new instance is created. So it's a little simpler, but more or less the same. Also, one more thing, when you are extending in Scala, you can extend from two traits, but always the first word is extends, and the second keyword is a with. And all the other traits that would come after the simple would be with. So first one is always extend, this is with. Otherwise, it works the same. And one very important thing at the end, as you can see, this variable, as the var keyword indicates, is mutable. This means it's a standard variable. Here we also have a val, and val is immutable. This is the equivalent of making a variable which is final in Java. So we have vars and vals. If you want to program side effects free and very functional, that basically means you don't use vars, if you choose to do so. Then also a very quick look at the type parameter syntax. Again, a very simple example of the Java method, which has a type parameter. Main difference, instead of the pointy braces in Scala, we use square braces for the type parameter. Otherwise, it works very much the same. Also, a small reminder, as I already mentioned, everything is an expression. So unlike in Scala, if is an expression, so it returns one of those values depending on the condition. In Java, you have to explicitly return from the method. In Scala, you don't have to. You can return from the method, but it is generally not recommended because return from method in Scala works much like breaking a cycle in Java. So basically, you break early. If a return is inside of a closure or a lambda, it will not exit the lambda, it will exit the underlying the method. So if you look at the Scala code everywhere, nobody uses returns anywhere. So it's just a backwards compatibility thing. A basic control flow. Yeah, so let's talk about some things which are actually missing in Scala or done differently. There are no checked exceptions. Everything is unchecked. Every Java checked exception is treated as an unchecked one. You can, of course, catch it, but you don't have to advertise it or explicitly catch it if you don't want to. I think this is also an improvement because people are converting check exceptions to unchecked in Java world all the time. There is no switch statement, but instead we have pattern matching, which is much more powerful. We will get to the example of that. And most importantly, there are no operators. This language has no operators. It's a functional language. Everything is a function or a method, everything. And how that works, so it still looks normal. You can write an expression like this, like string plus string, but this is a method invocation. This is not an operator. And why that works is for these two reasons. At first, we can have methods with symbolic names like this. Any kind of gibberish you want, you can put into method name, which sometimes makes up for really crazy domain-specific languages which you're going to implement in Scala. And also, there is a so-called point-free invocation style, also known from other functional languages, where you can omit the dot and also the brace and just like, on this object, I call this method with this parameter. This is exactly what it does. These two expressions are completely equivalent. And even the compiler might even complain if you do this, like, this is not necessary to put parentheses there and things like that. So you can actually choose. If you are programming, if you like the dot notation, you can go for it. If you don't, if you like the point-free style, you can go for it. It's fine. Another, I think, a very good thing, there are no primitive types. They're dead. So no primitive Scala primitive types. They have been replaced with the classic Java object-oriented types, except the integer was renamed to int. That's the only little surprise. Don't worry about the performance of these. There are tricks used in the Scala compiler and Scala standard library and the language itself that usually makes them perform really, really well. So, for example, one of those tricks is value classes, which is a mechanism that causes the compiler to convert these values to actual values which are being passed instead of passing the references. So these classes pretty much always work as values. So there is no overhead, in there. But you still get a really nice type safety. You don't have a special cookie in your type system that says, like, oh, this is not an object, it's something else. Everything is an object, it's fine. Everything is a proper type. And another funny thing, there is no classic for statement. You know, the iterative type, like starting with something, index, increasing the index, and then counting and executing a statement several times. There is no such thing, but it can be easily replaced or emulated by specifying a range, which will generate an iterator for this range, and then the for statement will operate just like the enhanced for statement in Java, which can iterate over all kinds of iterators and collections and things like that. So again, a simple example, classic for loop, enhanced for loop in Java, equivalent of the classic for loop in Scala, and the enhanced for loop works exactly the same way, except you have a different symbol here instead of colon. It's an arrow. This is also very common in other languages, that you don't have the old style for statement. There is still while loop if you are into that. Also, there are no static members of classes. So class can only have instance members, but there is a perfectly equivalent thing instead of static members. Scala has something called objects, and this is basically a language implementation of a lazy singleton pattern. So if you create an object, there is always the one instance of the object. You can reference the object, and you can put static, everything you put in the object is static, right? Because there is only one instance. And funnily enough, you might have something called companion object, which only means that you have created an object with the same name as some class. So these two can work together. And in reality, what this means that if you have a class data and object data like here, if you do data dot something, you are referencing the companion object and you are getting the static member. And if you do new data and put it into variable, then you are working with a class. So from the perspective of actual coding, the syntax works the same when you're using the object. Just when you're declaring it, you put your static things into the object and not into the class. Again, on the example, I hope this is a very simple example. You can see that this is an instance, this is a static member, this one goes here, this one goes to the object. Done. And perhaps actually the biggest change is there are some constraints for constructors. So in Scala, every constructor has to call another constructor first. It has to be the first line in the constructor. There's no way around it. And maybe this is the biggest change. There are good reasons for it. And if it sounds scary, it's fine because you can still work around it. As we already mentioned, we have objects. So if you have a constructor that it's supposed to call another constructor, but you want to do some computation first, some initialization, you can put that initialization code into a companion object or on another object and call it as a part of the expression which calls the old constructor. So this is a nice workaround that totally works. Practically speaking, from experience, this is not really a problem. I mean, you will not really hit this, like, it does not cause problem very often. This is fine. Okay, let's talk about integration of the two. So we are still very much deeply in Java features, but we have decided to write some code in Scala. So how do we do that and how do we integrate to the Java code? Because I'm assuming that since this is a talk aimed at Java developers, you all have a Java development environment, you have your tools, you have your Java, so you want to use it with Scala. First, let's look at the calling Java code. Well, nothing to say here really. The syntax is exactly the same. Nothing special is going on. Very important, if you can call any libraries you have in ClassPath, any classes you have in ClassPath, using exactly pretty much the same syntax, just with the little changes that we have introduced of syntax. So, for example, here, if you have a string and we call toString on it because that's super useful, and the string is a method that has no parameters, in Scala you can omit the braces, but you can also put them there. Depends. Generally, what people do is that they put braces after the method names to indicate that this method can cause side effects. So if it's a pure method, then they don't put braces there. So it's like a little annotation. But you can do it however you want. It doesn't matter. Then if you want to instantiate an object, classic syntax, just a different parentheses. So nothing very special to see here. We can extend an interface. We can implement a method. This is a method that does nothing. This means basically empty block. So this all works. Very important, you can happily have both Java and Scala classes in your project, in one single artifact or project. Your build system, all of those that we mentioned, can run both Java and Scala compiler at the same time. And this is actually straightforward because both of those compilers just produce classes. So they just run the compilers, produce a bunch of classes and pack them into jar. So this totally works, everything works, nothing to worry about. This is actually one of the really nice things that I like. The transition from Java development to Scala has pretty much no cost because you can use your project and just start writing Scala and it's going to be fine. Could be slightly more complicated if you want to call Scala code from Java code. So if you have a Scala code that doesn't implement any special features that the Java doesn't have, you just call that code normally again. So see, we have some class called called by Java. We can again instantiate in Java. There are two things worth mentioning. We talk about the non-existence of check type sessions. That's true, but sometimes you have a code that expects to call something that declares check exception. So for that in Scala there is an annotation which actually emulates the throws keyword in Java. So that we can say, hey, this method, if called by Java code, says it throws an exception. And another thing is that, as you might have noticed, the class properties are generated automatically, and it means that basically the accessor and the mutator methods for class properties are usually generated automatically. And they have some sort of mangled name. So if you want to call the automatically generated mutator method, you do it like this. There's a property and some suffix called equal. It's like equals. So this is very convenient. Normally you don't have to do this much, but if you do, this is possible. So this is instead of set property, we have property slash or underscore EQ. And here is an example of catching that exception from this method that declares it. So again, not many surprises there. One thing also worth mentioning is if you have a Java code, very often what happens is that you have a library you are calling and this code returns some sort of Java collection. And Scala collections are much more powerful. You usually want to work with them. So how do you convert? Or vice versa, you want to actually supply the Java collection to some library you're using. It's a very common pattern that on Scala projects you use like half Java libraries and half Scala libraries because it just works. So there is this little import called Java converters. This means this is like a star in an import. You import everything. This is a wildcard. And that allows you to take a collection instance and go .scala or .sjava, and it will convert them one to one. As you can see, we start with the Java collection, then we make a Scala collection out of it, then we prove that fact by calling something that doesn't exist in Java collection, so this is really a Scala collection, it's true, and then we can again convert it back. And this is the type that we end up with. Again, this is a Java util map. As you can see here, I have chosen to put a type annotation after the variable just to demonstrate the type. So if it would be wrong, the compiler would complain. Okay, and let's now talk about the interesting stuff, additional features. What does Scala bring you? What more power does it bring you? What extra? Why is it worth actually using it as opposed to Java? Let's start easy. String interpolation, common feature in many languages. You have a string, you want to substitute or insert other strings into strings. This is a very common use case. So you do this with a little S operator, but it's not an operator. So this works, but S is not the only one. This is actually implemented in Scala standard library. This is not a language construct. This is a method. And there is another one called F, which does the printf formatting. And then there's another one called row, which does the no escaping formatting. So you can put the non-escape special characters there. And as you probably have already guessed, this is all programmable. Let's say you import some external library that has a different string interpolation method implemented, just like, for example, creating a JSON out of string. Very, very nice. So this all works. There are libraries that implement the things. Like, for example, there is a neat library that allows you to do this with SQL statements. You insert, it's a classical problem of inserting things into SQL statements safely, so that the escaping is right. So they have an SQL string interpolation method. that formats the entire statement, and so on and so forth. This is very nice. It leads to a less verbose code. It's very easy to read. So this is easy. Now let's take a small detour to Python. People who know Python, you can ignore this slide. Just like in Python, we have useful things like named arguments, default arguments, and tuples. This probably requires not much explanation. We have a method. There's one argument is standard, another is default, has a default value. If we call that method only with one argument, this is already provided. So, and then we have a different method, which is the same thing but in a different order. So the problem is now how do we call it? We can name the argument, so we can specify that we only supply the second argument. It doesn't have to be in order. It's specified by name, and then the first argument is inserted automatically. And then tuples, well, that's quite easy. So tuples have exactly the same syntax like in Python or many other languages with round braces. So I can have a method that accepts a tuple of different types, and then it returns the first member of the tuple, first item. This is the syntax for referencing items in tuple, because there are not enough underscores in Scala, as you will see later, so they put an underscore in there. Then if you want to create a new instance, it's again the same instance with values, and then you can call this method with this new instance. So this is very useful, I would say, low level, but very, very programmer friendly stuff. Let's look at a little bit at scoping. What I would like to say about this part is that this whole slide means that if there is something you can't put in some place in Java, you can probably put it in that place in Scala. So there are less restrictions. You can have fields in traits, like this. So this is the abstract field, it's not defined, and it's not a method, so you can have that. You cannot have that in interfaces. You can also have an abstract, standard abstract methods. Again, as you can see, you define abstract method, not by saying it's abstract, but that's simply not implementing it. You just put it there, it's just like an interface, and it's an abstract method. So the traits are a little more powerful than interfaces in Java. It's a bit more flexible. And you can have nested function definitions. So you can put functions and values pretty much everywhere. So just like you put a local variable into a function, you can put a local function into a function. Nothing special to see there, it just works. And then, of course, if you have a function inside a function, then you can call it from inside and return the result. So this is basically stuff that you don't need to think about. You can organize your code pretty much in any way you fit. It's probably not going to complain. Okay. Now let's look at a bit more high-level features. We are slowly entering the functional territory of the features of typical functional languages. Pattern matching. This is a very powerful feature found in many functional languages because it provides object decomposition. So here we have a little method that is tries to describe some sort of value, and the value is of type any. We don't know what it is, or at least at the compile time we say we don't care. And it's supposed to create some description. So we take a value and we match against it. And if you know, for example, Haskell, this is a very common pattern. And then we can match many things about it. We can ask if this is a concrete instance. So is it 2? Oh, sorry, 1. Is it 1? If it's 1, then it's 1. Good, great. Or if we say, well, we want to see if it's an int. And then we want to bind that instance into X so we can print it out. Again, string interpolation strikes here, as you can notice. Or we can say, well, okay, if it's a double, and there is also a guard statement, so it's not just any double, but this double has to be less than something, has to fulfill some sort of condition. So then it says it's a small double. So this pattern matching can be very powerful. You can put all kinds of guards in there. It certainly beats the old school switch statement. It's really like switch statement on steroids. Or we can say, hey, we actually don't care about the value, we just want to know the type. So we put the underscore instead of the variable, the instance name, because we don't want to bind it. So this just means that something we don't want to name, it's there, but we are not going to use it later. This is typically underscore in Scala. It either means everything, or it means something we don't want to name, because we are not going to use it. And we have a little or here. So it's like if it's float or double. So as you can see, you have conditions, and you have also disjunction. And then we said this is a floating point. And the last but not least, this is the default statement. So again, case if it's something we don't care about, anything, the underscore strikes again, then it's this is the last option. This is the catch-all. A little example how that works in practice. Yeah, so this is the pattern matching using match statement. But here's the thing: in Scala, pattern matching works automatically for every class that has a companion object which implements an unapply method. Unapply method is the decomposer of the class. So if you make your own class, you implement unapply method, you can do this stuff with it. And even more, because your class can have a structure, like a tuple. It consists of two things. And we can decompose, this is also, by the way, possible in Python. We can say, hey, I want to set this instance, I want to decompose it into two variables, and this will generate two vals with the members of the tuple. And you can do more. You can do this with like collections, like vectors. So yeah, this is a vector of 3 items. It's like first item goes to the first, second item we don't care, we ignore it, and the third goes into third. So again, this is a classic pattern matching decomposition. Or even more, this is a special thing. If you have this works if we know how many items are in the collection, because we are matching exactly. We are saying this thing will have 3 components, not more. Here, this syntax, as you have probably guessed, allows us to match some first component or several components if we name them, and then the rest. So this magical blob here, the at and whatever that is, underscore star, tells you that I want to match the first item in the list and the rest. So the first will be an item and the rest will be the rest of the list. So there are many other examples like this. Pattern matching is extremely powerful. As you get into Scala and as you start being good at Scala, you will pretty much stop using if statement, because most of the things can be done with pattern matching in a less verbose and more safe way. Not saying like you will not stop using it completely, but really you will use pattern matching a lot. Case classes. This is a natural thing to say to mention after the pattern matching. Case class is basically a little language construct, a convenience feature, I would say. It's a special type of class that makes the compiler generate things for you. And what it generates is actually generates the equality method, which works by comparing the properties. So this is basically the typical data holder idiom. You want a class that holds data, and if you have 2 instances that hold the same data, you want them to be equal. This will generate the code that will compare them. You don't have to do it by hand or with some, sorry. Oh, this is working. You don't have to use any framework or anything. It will also generate a pretty toString where it will serialize the properties of the class. This, of course, works recursively. So if you have a case class inside the case class, it will be nested, it will all work, it will compare it correctly. And it also generates apply method, which can be used for various things that I'll mention later. And also the unapply, as we mentioned, this is the decomposition. So that means that if you have a case class, you automatically, as you say, we have an unapply method. So we can pattern match on case classes. This totally works everywhere. So a common idiom is that if you want to just hold some data, store some data, you are going to create a case class, and then you can pattern match on it and compare it, and it's just going to work very nicely. From the type theory point of view, this is basically an implementation or one form of algebraic data types, because you have products, you can have multiple properties in one class, do that together, or you can also have union. There is an example for this. Union means, well, just like if somebody remembers in C, you could have union, a type that represents a one type or another, depending on the instance. And you could do the same thing. You can declare a so-called sealed trait. That means that this trait cannot be inherited from anywhere else than from this file. So this is a finite subset. And then you can declare 2 case classes, which represent different subtypes. And here we are modeling the classical binary tree. As you can see, we have a leaf and we have a node that has other left and right children, and all of that is tree. And then you can pattern match on this stuff. So let's say we have 2 trees. They're the same. We can compare them. This will be the invocation of the equals method. Actually, oh, this is also one difference, that this will actually invoke the equals method. This is not the comparing of the indices. So those 2 trees will be the same. Then we can construct another tree, just like this. We don't need a new keyword, because I mentioned the so-called apply method is already generated by the compiler, and it means that constructing a new class works like calling a function. This is the reason why it's there. So new is perfectly fine, but if you want to pass around functions and lambdas and closures and these kind of things, it's very nice to have a functional construct for instancing, creating a new instance. So doing the node something is just like the new node, but this is actually a function. So you can construct a new tree here. As you can see, it has one left leaf and another subtree on the right. And now I want to pattern match on that structurally. So I want to pull out the value of the left node. I can totally do that. I can say, well, this variable, it's supposed to be a case class of type node, and inside it's supposed to have a leaf on the left, and anything on the right, I don't care. Again, I put an underscore there. This is the part I don't care about. And that leaf is supposed to have a value. So the value of 1, which was constructed here, will be bound to this identifier. This is quite nice. So this was about pattern matching and case classes, which are using the mechanism directly. Now let's look at, and maybe this is the most important slide, for comprehensions, or so-called comprehensions. So you remember how I said that there is no classic for loop in Scala, but only enhanced one. Well, I have a bad news for you. There's also no enhanced for loop. There is no such thing. This is only syntactic sugar. They killed the for loop for a good reason. So if for loop is actually just a syntactic sugar for monadic function composition, which sounds scary, but it's not. If you are familiar also in newer version of Java with functional-ish method, just map as flat map, this is what it really does. So for example, we have here the 2 collections. And this is a simple example here. We just iterate over a collection and add 1 to every member. Well, what this really does, it calls a map function. So it maps over the entire collection, and it executes this lambda for every member of the collection. This is what the compiler translates this statement to. These two are completely equivalent. If you look at the bytecode, this is what you will see. This is only syntactic sugar. This is very much similar to, like, for example, in other languages like Haskell, which has a syntactic sugar also for some monadic constructs like do and things like that. So it's just a very nice way to write it, which is quite recommended. We can also look at more complicated examples. So you can actually compose these things together. You can have a guard in there. So let's say we want to iterate over 2 collections. So we can iterate over the first one. Then we filter. We only say, oh, we only want items which are less than 3. Okay, fine. And then at the same time, we want to iterate about the other collection. And then we want to combine the results. So this will create a Cartesian product of the 2 collections, except it will leave out in the first collection the items which are less than 3. And again, in reality, this translates to a chaining of a flat map and map operations. This might look cryptic, but trust me, after working with in a functional way, this will be a second nature. So the flat map has to be here because this map creates a collection, not an item. So we need to flatten that. If we would have 2 maps, we would have a collection here, and then another collection of collections. So we need to flatten that. So that's why flat map. It first maps and then flattens. So this is what really happens with these 4 statements. And this is really the thing, if you want to work in Scala, really good thing to internalize. Okay. Implicits. This is another really nice feature, which is actually not found in many languages. Classic problem, you are performing some operations, you have a nested chain of functions which call each other, and you need some sort of context that you need to carry around, like, I don't know, some sort of database transaction and the different frameworks in Java solve this in different ways. You have magical thread local variables and things like that. So Scala supports automated passing and conversion of method arguments. That means that you have a method that has an argument that also has an implicit argument. And if you don't specify the implicit argument, the compiler will look in a scope, or in imports, there is a certain succession of places where it looks for implicit value. And if it found it, it's going to put it in there. So then, in effect, this call and this call are equivalent. If you don't put an implicit argument in, it will find it here. But you can also put it there explicitly. It's fine. And by the way, as you notice, this method has two argument lists, but that's the only difference. You have to do this when using implicit arguments. It cannot be used in one argument list. A little more advanced use case is implicit conversions. So instead of just passing some value that is in scope to a method as an argument, we have a problem that this method this method here, it requires an integer offset here. But what if we don't have an integer? So what can happen is that we can have an implicit conversion. If we define a method in scope, which is an implicit method, which takes something as an argument, some different data types, and produces integer, which is the right data type that this other method needs, if it's implicit, and then the compiler can find it, it can automatically call it and convert the argument to a right data type. So as you can see here, you can just call the more method with vector, and it will find this conversion function. Oh, this is a vector, I have a vector, I can produce int. So in reality, what happens, it will do this. It will first find the convert, it will convert the vector, it will insert the converted argument, which is of the correct types, and then it will also insert the other implicit value, by the way. So this is a very nice feature which has other use cases, but we don't have enough time to go into that. And another very important feature, especially in functional context, is lazy evaluation. Scala doesn't really support lazy evaluation natively. I mean, not in a full extent, like in some other pure languages that everything is lazy, for example, Haskell, but you can quite easily emulate it. In Scala, evaluation is eager, just like in Java by default. So whenever you pass an argument to a method, it will be evaluated before the method code is executed. An example of that is here. We have a method. We have a method here, and before we get to this point, integer is evaluated. Whatever comes to the argument is evaluated. Another option is to use a so-called call by name syntax, and this is the opposite. If you just put a little arrow here, this means that Scala will take the entire expression that was inserted into the method, and it will like substitute the expression inside. So if this was a complicated expression, it looks like if this expression would be just put here instead of input. So the evaluation only happens once the expression is actually used inside the code of the method. This is classical call by name. It's a pattern rewriting paradigm. But this becomes useful usually only when we can convert it to so-called call by need. Call by need is exactly the same thing as a call by name, except we memorize. So that means first time we evaluate the argument here, we can declare a lazy val and put the input, whatever expression this is, into the lazy val. And as you can probably guess, lazy val will be then evaluated only for the first time. Every time, every next invocation, this lazy value will be already instantiated, and the value will be reused. So if you want to have a Haskell-like lazy evaluation that everything is only evaluated for once, but lazily, only when it's really needed, this is the way to do it. So this is the little pattern. Okay. Since this is an introductory talk, we don't really have much time to dive into many other Scala's advanced features because there are quite a lot of them. So we can just go, we're just going to provide a quick overview what is there. The next 3 or 4 slides will be basically the Googling material. This is a nice list. If you want to learn more, you can Google for these things and find examples and learn how they work. So just quick, we have a partial function invocation, just like, again, many functional languages, you can invoke the method by specifying only certain arguments. And then the invocation will create a method, will create another method instance, another closure that requires the rest of the arguments that you did not specify. This can be also in Scala achieved in 2 ways, either by currying or by partial functional invocations, but the point is that it's possible and it's very easy. Another very useful pattern is type classes. You might have heard about it, or maybe you are using them. Type classes are simply a way to enrich a functionality of an existing type without extending it. Very useful if you have a library you can't subclass or whatever, but you want to enrich the functionality when you're using it. Type classes are just for that. Again, very popular feature in Haskell. Maybe you are starting to see the pattern in Scala. It likes to reuse the features in Haskell, which is a good idea generally. A little surprise maybe, Scala actually supports dynamic type checking. There is a construct for it. If you make an object that implements so-called apply dynamic, you can have your Ruby in your Scala. Totally possible. It can be useful for some things. And also there are macros. Macros are basically a way to perform compile time reflection and code generation. This is a very powerful feature which many Scala libraries and frameworks use to generate all kinds of useful constructs and use to simplifying the code. You can think of like what you achieve in Java normally by heavy bytecode instrumentation, frameworks like Spring do these things. You can probably do with macros in Scala, and it's much more cleaner because it's checked at compile time. Everything is safe and generated at compile time. So this is very powerful, something very powerful that worth looking into. And now just a really quick overview of the type system. I have on purpose not mentioned much of the type system in Scala because this is really another talk. Time system in Scala is extremely powerful. It's one of the most powerful of the commonly used languages, even not the, if not the most powerful. So there are so many features in the type system. You can do full-fledged type level programming, so you can actually do, you can have type system itself run at compilation type is basically an implementation of lambda calculus. It's computationally complete. You can do really crazy things. This is the stuff that you maybe normally don't need, but sometimes you do. So it's good to look it up. Very many very useful features. You can have compound types. You can have mixing class composition that solves the diamond problem, which is found in some languages. You can alias types. You could have abstract type members. You can have different ways to, you have these type expressions, not just specifying a type in type annotation or type parameter. You can have a whole expression that allows you to specify exactly what kind of type it can be and how it should behave. It's really, really powerful. You have type variants, view of context bounds, existential types, type self-references. Oh, by the way, you can have structural types. This is basically anonymous type. So you can say like, hey, this type is not referenced by name, but I want this type to mean any instance that implements this particular method. These are like anonymous type. This is not by the way, this is not duck typing because it's checked at compile time, but you can basically just say, I don't want to name this type. I just want to say this method has to exist in this type. So this is quite useful sometimes. And last but not least, even more advanced things like type lambdas, again, more expressivity in type parameters, f-bounded types, which are self-recursive. So this is like really, you can have a recursion at compile time in your type system if you want to do such a thing. Higher the types, of course, you can have types that construct types. You can have a type constructor of an infinite abstraction level, value classifier. And these two features are used for more efficient implementation of primitive types that doesn't actually break the rest of the type system. Okay, and that's it. So thank you. Hopefully the overview was useful. If you didn't catch something, don't worry about it. I guess the slides will be online, and this is really should, at least these few last slides should work as a reference, not as an in-depth overview. So if there are any questions, please ask. Also, I hope I wasn't going too fast, but just so many interesting features. You can't help yourself.
Thank you very much. Any questions? Raise your hand and you'll get a microphone. Or, you know,
who still has the energy to ask a question after all day?
Alternatively, now there's beers downstairs, so you can always find Martin and ask questions in a one-on-one.
I love to talk about my experience in Scala, and like it's really.
Thank you very much.
Thank you.
Give a round of applause.